Let's talk about ethers. In this video specifically, what I'm going to be talking about is how we name ethers, their physical properties, and how we make ethers is pretty straightforward, and actually we're already familiar with these reactions. We're just going to introduce a new term to describe these kinds of reactions called the Williamson ether synthesis. You may have heard of ether in a medical context before. It's actually ether has historically been used as an anesthetic for over 100 years. The ether functional group actually is an oxygen that's bonded to two different carbons, as it is in this molecule, which is THC. You can see THC has an ether functional group and an alcohol functional group. So ethers are found in biological systems and can have significant biological activities, either as anesthetics or as recreational drugs. Okay, so as I mentioned, ethers are related to alcohols in a way because they contain a R group bonded to an oxygen, but they actually have two R groups bonded to the same oxygen. So for example, this is dimethyl ether. Some other ethers that you may or may not have heard of before. This is called diethyl ether, which is commonly used as an organic solvent, especially in Grignard reactions that we've talked about. This is often abbreviated as ET2O, for example. This is tetrahydrofuran, or THF. This is also used a lot as a solvent in reactions. Anisole is another ether that you may have heard of before. It's found in the anise seed and has kind of a licorice flavor or smell to it. One thing that you'll notice about ethers that I'm going to emphasize in this video and in future videos is that ethers, for the most part, are pretty unreactive. And for that reason, they make really good solvents for organic reactions. So Grignard reagents, for example, are extremely highly reactive species. You have a negative charge on a carbon. It really wants to react. And so you want to choose a solvent that's not going to react with those species. And that's why, because diethyl ether and tetrahydrofuran are very inert, they don't really undergo organic reactions readily. They make ideal solvents. Okay, so how do we name ethers? I'm not going to be too worried about you knowing this, but for the most part what you'll hear is that you just name each alkyl group in alphabetical order. So for example, this particular compound would be called ethyl methyl ether. This would be called tert butyl methyl ether. We ignore the tert when we're naming these things in alphabetical order. Another way that you can hear these things named is that you can name the smaller group as an alkoxy group. So the longest chain here would be 1, 2, 3, 4, 5. So this might be named as ethoxypentane or as ethyl pentyl ether. Those are two complementary ways of naming these things. Most commonly you'll see dimethyl, diethyl, dipropyl ether, things like that. Okay. What are the physical properties of ethers? Well, they're somewhere in between that of hydrocarbons, which don't have any polar bonds, and alcohols, which have hydrogen bonding. Because we have dipole-dipole interactions, these molecules are polar, but they're not as polar as alcohols, so they have relatively low boiling points compared to alcohols. For example, ethanol has a boiling point of 78 degrees, whereas diethyl ether has a boiling point just above room temperature. Dimethyl ether is found in these wart remover types of systems, which just freeze the wart, this is gross, and make it fall off, right? That's because it has an extremely low boiling point, so the evaporation of that causes it to get really cold. So obviously, as the length of the alkyl chain increases, the boiling point also increases. Okay, so how do we make ethers? We're already familiar with these reactions. Williamson ether synthesis is a fancy way of saying SN2 reaction. Right? We know how to make ethers. It's just that we haven't explicitly thought about this before. The Williamson ether synthesis was invented, of course, by a guy, a dead German guy by the name of Williamson. How do we make, let's say we want to make diethyl ether. one way to do it is to start with ethanol. And this is not a great nucleophile, and we need to make it into a great nucleophile if we want to do an SN2 reaction. So the first thing we do is we treat it with a strong base. We've talked about the different bases that we can use to depronate alcohols. One of the easiest ones to use is sodium hydride. So this is a common choice when we're making an ether. So sodium hydride will remove this hydrogen. So instead of having an alcohol, now we have an alkoxide. This is a much better nucleophile because it's negatively charged. Okay. Now we need to add an electrophile. I'm going to choose ethyl bromide because I want to make diethyl ether. Now we're going to have our SN2 reaction. And notice that we formed a new bond between oxygen and carbon. So now we have this is the bond that was formed. So notice, first you remove the hydrogen to get a good nucleophile. Then you add whatever group that you want, the alkyl bromide, to put on the second R group. You already have one R group in your alcohol. You're putting on a second R group in your Williamson ether synthesis. Okay, seems relatively straightforward. Where could we go wrong? Well, we could go wrong because remember, SN2 reactions and E2 reactions are always competing with one another. So let's say that we want to make MTBE, methyl tert-butyl ether, right? Anytime you see an ether, you want to think backwards to the two R groups. We could theoretically make this bond between oxygen and carbon, or we can make this bond between oxygen and carbon. But let's look at the two possibilities. In the first case, if we treat tert-butanol with sodium hydride, we're going to get tert-butoxide ion, right? This is a sterically bulky base. We would expect this to carry out an E2 reaction. The nice thing about methyl iodide, it doesn't have any beta hydrogens that could eliminate. The only pathway available is an SN2 reaction. Voila, we get MTBE. But let's look at the other possibility, right? If we take sodium hydride and react that with methanol, we get methoxide. Remember, that's a strong base which is not sterically hindered, right? But this is a tertiary halide. And so if we have a strong base interacting with a tertiary halide, what's going to happen is that the E2 pathway is going to predominate. So we're not going to see any SN2 reaction. We're just going to see E2 reaction. We're not going to get the ether that we want. We're going to get an alkene, right? So the moral of the story here is that you should, for Williamson ether synthesis, always select a methyl or a primary alkyl halide for your group. So this is a methyl, this is tertiary. So we need to tack this piece on instead of this piece because that would undergo elimination. Let me show you another example. So let's say that there's more than one way to skin a cat, right? So another way to make MTBE is through an SN1 reaction, right? We could take tert-butyl bromide, treat it with methanol. The bromide would leave, we're familiar with this, to give a tertiary carbocation, which could then be attacked by a lone pair of electrons on methanol. That's going to give us an intermediate that looks like this, right? We have a protonated version, and then another methanol molecule can accept the proton to give our product. The problem with SN1 reactions is that they're pretty slow, and so that they're not generally used to make ethers. Usually you're going to choose Williamson ether synthesis if you have a choice. Okay, so let's look at this practice problem, right? We want to make this ether, and so the way you want to think about this is thinking backwards. Use retrosynthesis, right? There's two different bonds that we can form in this ether. We could form this bond theoretically, or we could form this bond theoretically, right? If we think about the two possibilities, let's say this is bond A and this is bond B. If you think about bond A, right, we would have some kind of a halide, let's call it a bromide, and an alcohol. Notice this one's secondary, so we would expect elimination in this pathway. Let's look at bond B. Well, now we're forming this bond, so we started out with a secondary alcohol and a primary bromide, which is not going to undergo elimination, so this is probably the best way to do it. Since this will favor SN2 pathway, this one would not give us what we want. It would give us an E2 pathway instead. So in the forward direction, let's think about how we would actually propose the synthesis of this particular ether. What we would do is we would take, we would take this alcohol, first treat it with sodium hydride. That would create the alkoxide here, and then we would add a primary alkyl halide, such as this one, which would get us the ether that's shown. So this is the best way to make this particular ether. If you have a choice, you always want to use a methyl or a primary halide. Okay, so to summarize, we define ethers as compounds that contain an oxygen bonded to 2 carbons. Currently and historically, these have been used as anesthetics. Don't worry so much about the naming. I just want you to be familiar with the naming, so if you see the name, you know, okay, that's an ether, and I know what that looks like. Know how to name these very simple ethers for the most part. The way that we make ethers is by Williamson ether synthesis, and be very careful when you're planning these syntheses. You always want to use a primary or a methyl alkyl halide for your Williamson ether synthesis. You can also propose SN1 reactions of tertiary halides with alcohols, but it won't work with alkoxides, right? That's an E2 reaction.